In this video, we're going to talk about the kinetics of radioactive decay, as well as fission and fusion. So let's begin by talking about the kinetics of radioactive decay. This all happens and follows the same math as other first-order kinetic processes, which we've talked about in previous lectures on kinetics. And for first-order kinetics, we said, well, the rate of some first-order reaction equals the rate constant for that reaction times the concentration of that reactant to the first power. And that's it. And that's what makes it first order. And we were able to use that to derive this equation of integrated rate laws, where the concentration at some later time can be predicted if we know the rate constant, the amount of time that's elapsed, and the initial concentration of that reactant. Okay, so we've talked about this in the context of reactions. But a nucleus undergoing radioactive decay follows the same kind of process, where the number of nuclei, so it's not a concentration anymore, but just the number of nuclei that are going to be found at some later time t, can be predicted if we know the rate constant for this decay process, the amount of time that has elapsed, and the starting number of those nuclei, which we'll call n0. We can rearrange this, subtract ln of n0 on both sides, and use the property of logs to turn it into this form. But both of these are analogous. And so when we're thinking about radioactive decay and thinking about how many atoms of uranium-235 there are going to be after a couple hours, if we start with a certain amount of uranium-235, we use these types of equations. We also had this term for half-life in kinetics, the amount of time it takes for the concentration of the reactant to be cut in half, or here for the number of nuclei we start with to be cut in half. And for first-order kinetic processes, this is equal to natural log of 2 over the rate constant. So here are various half-lives for various isotopes. Here's uranium-235. That's half-life is 7 times 10 to the 8 years. Really long time. So it's a slow decay process. But other things like carbon-14, 5,700 years. And the types of decay for each are listed here as well. This is just extra information to give you some context here of what half-lives look like for various decay processes. But these are the equations we can use to exactly predict things like how much will be left at some later time. And so the half-life for the decay, like all first-order kinetics, doesn't depend on how much of the nuclei there is to begin with, right? Nowhere in this half-life equation, okay, which we've just reorganized a little bit from the previous expression I wrote, but these are the same thing. Okay, nowhere in here is there initial concentration or initial number of nuclei, right? It doesn't matter how much you start with. The amount of time it takes to be cut in half is the same, just depends on the rate constant. Let's review a little bit just the concept of half-life and try this practice problem here. Feel free to pause the video and try it yourself before I start to solve it. Okay, if we start with a 50-gram sample, how much of that sample remains after 3 half-lives have passed? Well, after 1 half-life, that 50 gets cut in half. After the second half-life, that 25 gets cut in half. And after the third half-life, that 12.5 gets cut in half. So after 3 half-lives, we should have 6.25 grams. Okay, you don't have to do any more complicated calculations than that. Now, to give you an example of how we can use these formulas in a practical way, we can do radiometric dating. All of this first-order kinetics for nuclear chemistry we've talked about here can let us date objects using this nuclear clock. So since the half-life for these nuclear processes are constant, we can use it to determine the age of objects laying around us. Okay, this is known as radiometric dating. If the exact isotope we're using is carbon, and specifically carbon-14, then we call it carbon dating. And that's maybe the most famous example and one you've heard of before. The half-life for carbon-14 is 5,700 years, roughly. And so you can carbon date things back to 50,000 years or so, and then after that, there's simply too little carbon left, it's all decayed, to get a good representative of the age. And so you can use different nuclei. It's not called carbon dating, it's still radiometric dating, but using a different nucleus. So you could use uranium-238 or lead-206 that's found in some rock to date it. And so what does this look like? Well, you could find some old piece of wood laying around, and you could measure how much carbon-14 is in that wood. And you'll say, okay, that is the number of nuclei after some amount of time t that wood has existed. You can find a similar type of wood, but that is from a fresh tree, so it's new, and measure the carbon in that. And that'll approximate N0, right? When that old wood was actually new, what was the amount of carbon-14 in that? And then if we know the half-life of carbon-14 is 5,700 years, well, let's look back at our equation. Now we have NT, we have K, right? And we have NO. We have K because we have the half-life and we know natural log of 2. So we can use our half-life to calculate K, plug it in here with our values that we've measured from the old piece of wood and the new piece of wood, and solve for T. And that'll tell us how old this old piece of wood is. Right, so we'll take the natural log of that old piece of wood's carbon, the number of carbon-14 nuclei on that, which we can measure with mass spectrometry or some other analytical technique. We can plug in our rate constant K, because remember, K here is ln of 2, 0.693 divided by 5,700. That's how I get this number in inverse years. And we can measure a new piece of wood and its number of carbon-14s and plug it all in and solve for T. Okay, now this all only works if the element amounts in these types of objects are constant over long time scales, right? Because we're using two different pieces of wood here. But the assumption here is that, carbon-14 is based on the sun and our atmosphere and how plants grow. And that's relatively constant, how that's been happening over tens of thousands of years. So we sort of assume here that the carbon-14 has been steady in our atmosphere. It's been steadily used by plants. And so using an old and new piece of wood, well, that wood is sort of growing up the same way 10,000 years ago as it is today. And so this is a safe assumption that the amount of carbon-14 has been relatively constant and used the same way in that wood. But here you can see how we can actually radiometric date things. Now, the second concept we have to talk about in today's lecture is the actual energy involved in nuclear reactions and demonstrate just how much it is. It's a tremendous amount. Okay, way more than is found in, say, burning methane, okay, or combusting hydrogen or something. Way more energy is stored in nuclei than there is in chemical bonds, right? And that's the difference here. Nuclear energy is about the nuclear processes and radioactive decay, whereas chemical energy is breaking bonds between atoms. Nuclei store way more energy. And in nuclear decay, there's a change in mass involved. We had this formula earlier where we saw uranium-238 in a previous lecture decay to thorium-234 by alpha decay, right? Which is essentially a helium nuclei that goes shooting out of the uranium-238 nucleus. Okay, and so then there's a mass change associated with that. And if you imagined you had a mole of uranium-238, so not a single atom, but a mole of those atoms, all decaying by alpha decay to thorium-234, the amount of mass that has been lost from all of those uranium atoms collectively is negative 0.0046 grams. And that is related to the energy involved in that process by Einstein's famous equation here, E equals mc squared. And so as long as we turn this grams into kilograms, we can plug it into this formula, including the negative sign here because the mass was lost and emitted, and plug in our speed of light, 3 times 10 to the 8, that is our c here. We can calculate that there was negative 4.1 times 10 to the 11 joules involved in that process. And the negative sign means it's emitted, or that energy is released. And here it's released as heat. 410 billion kilojoules is a ton of energy. It's so much. Okay, 1,000 times the energy you would get from combusting a mole of methane, right? And lighting this on fire and burning it, you get 50,000 times the energy from a mole of uranium-238 decay than you do from a mole of methane burning. Okay, and so if you could harness this energy, you could power 10,000 homes for a year just from 1 mole of uranium-238. Let's try a similar problem. We'll use E equals mc squared here to calculate the energy involved when cobalt-60 undergoes beta decay. Take a moment, pause the video here, and try this yourself before I solve it. Okay, first thing is to put this grams into kilograms, right? So this will become, let's move this decimal 3 places to the left to get it to kilograms. Good. And now we can plug this in for m. We can plug 3 times 10 to the 8 in for c. And just make sure you notice here that the mass is decreasing, right? This beta is being emitted and leaving, so this mass is actually going to be a negative 0.0003030 kilograms. Multiply this by the speed of light, 3 times 10 to the 8 meters per second, and that gets squared. All of that should give you negative 2.73 times 10 to the 11 joules for answer A. So much energy stored in nuclear reactions, right? Where we're talking about changes in the nuclei of atoms and radioactive decay, changing into new atoms, and there being a mass loss involved. Way more than just making and breaking chemical bonds. And that's why we try to harness this energy, because it involves such small amounts of matter and you get so much energy out of it. That's how we get nuclear energy. And so nuclear energy is based on a particular fission process, one shown here, and actually one other type, but this is the main type. And uranium-235 is pretty unstable, but in order to decay, you can give it a little nudge. If you have a little neutron you can throw at an atom of uranium-235, then it'll decay when that neutron collides. So imagine you have a little neutron gun and you can shoot this neutron gun at uranium-235. This neutron bullet then causes the uranium to split apart. You wind up getting various types of nuclei out. Those are fission fragments, and this is nuclear fission when a nuclei is splitting into multiple atoms. And you also get out some other neutrons. All right, so this is uranium-235 undergoing fission. Now, imagine you take these neutrons and put a new uranium-235 atom right here that this neutron can bump into. This uranium-235 will then split and release more neutrons, 3 of them. And you could place more uranium-235 for those neutrons. This gives us a chain reaction. So by initiating this fission process for uranium, which also releases more neutrons, each of which can go on and bombard a uranium-235 itself. Well, if you could have enough uranium-235 around, you could take advantage of all of these neutrons to just start the reaction and then have it self-sustain. Okay? and that is a chain reaction. A bombardment of this uranium-235 with a neutron starts the process, and then those other neutrons released in that transmutation, where we're changing one type of atom into other atoms, well, those can strike other uranium-235s and causing them to decay, and so on and so forth. So you need enough uranium-235 close by to sustain this chain reaction, and in fact, that has the name critical mass. If there's not enough uranium-235 around, well, the neutrons just go whizzing off into space and don't hit anything, don't cause these subsequent reactions. But once you have a critical mass or enough of that uranium-235 around, well, then those neutrons do end up finding uranium-235s and sustaining this chain reaction. Now, if you have too much uranium-235, you can get this runaway energetic event where you get an explosion. And that's how things like atomic bombs were created. You can take two safe subcritical masses and combine them together. You use this other separate sort of chemical explosion that forces these two halves of subcritical masses together to make a supercritical mass that then explodes with this runaway chain reaction because you have so much uranium-235 around to sustain this reaction. And each decay releases lots of energy. So this runaway process, if this was, say, 64 kilograms of a supercritical mass, it's able to release an equivalent of 16,000 tons of TNT. Okay, and that's what happened August 6, 1945, when the bomb Little Boy was dropped on Hiroshima. Okay, so we need to understand the chemistry and physics involved here and how they can be used for things like weapons, but also because we also want to harness them for just energy, okay, to use something beneficial like power the things around us. And so this same chemistry and physics is what drives nuclear energy in nuclear reactors that we have today. We have a critical mass of uranium in the reactor that we can use to sustain this chain reaction and release this energy that heats water, turns it into steam, and that steam turns a turbine which generates electricity and sends it to our homes. The critical part of this is the reactor core here and the control rods. So I just want to spend a moment on that. You have the uranium-235 in this reactor core in the form of these fuel rods shown here too. So this is where the nuclear fuel is. And these are critical masses that can sustain reaction, release neutrons that are going to hit other uraniums and sustain a chain reaction. But you also have these control rods shown here that you can move into or out of this critical mass area. And those control rods are really good at absorbing neutrons. So you can use that to sort of mitigate the chain reaction from happening. And usually those are computer controlled, but they can be overridden and controlled by humans, because what you don't want to happen is there to be sort of supercritical behavior and this become a runaway chain reaction. So you have these control rods in there to absorb some of the neutrons to quench the reaction and prevent it from running away. Now, that is all nuclear fission, where one nuclei splits into two. The last concept here I just want to briefly touch on is that you can have nuclear fusion. You can have two atoms, nuclei, fuse together. And these are sometimes called thermonuclear reactions. And even more energy is released in these processes than in fission. And if we could sustain fusion reactions, which we're starting to make some progress on, it'd be a great source of energy. Hydrogen is a readily available source. The products, when you fuse hydrogen together, you get helium, okay, which is a lot better than the nuclear waste of uranium that we're using now for nuclear fission reactions. The problem is atoms don't want to combine, and so you need extremely high temperatures and pressures to force them together, okay? This is what happens in the sun, where you can have such high temperatures and pressures. And you can design weapons that use fusion and thus are even more powerful bombs, fusion bombs called hydrogen bombs, which are 500 times stronger than fission bombs and never been used in war, right? But all of this represents sort of the double-edged sword here of understanding fission and fusion and how we can use these to power the world around us or create weapons. Okay, so I think we'll stop there. In this lecture, we discussed the kinetics of radioactive decay, as well as fission and fusion. That'll do it for this lecture. Bye-bye.